to a parallel first, right? So that means here, trying to get to RT, right, I'm going to have 1 over 5.2 plus 1 over 3.5 equals 1 over that R. Yeah? So whenever you solve that around, you add the 2, and then you take the inverse, that R comes out to be what? 2.09? Okay. 2.09. Now, and I'm not redrawing the circuit for the sake of time. I think some of y'all are getting pretty comfortable with this. Okay. So I squish these two together. What do I do next? Add the combination of these two, right? I combine the 5.2 and 3.5 together. Now I have a series between those two and my 7.8. How do you add resistors in series? You just add it. So this is plus 7.8, which gets me up to my 9.89, if you will, or 9.9 ohms. So that's great here. Now I've got a RT. So EMF equals I times 9.89. We'll worry about sig figs at the end. Plus my internal resistance I gave you was 1.3. It's 1.3. The only thing missing here is the current coming out of the battery, the red line, if you will, here. Okay, I got to figure out the current coming out of the battery. The red line, it sure is at 2.3 amps. That's after I divided it only in one of the legs. Now, if I could figure out the current coming through this leg, if I could figure out the current through that leg, I could add 2.3 plus that current and get the total current, the red line, the current coming out of the battery. Everybody get that? Current divides in parallel. Here's how I want to go about doing that. Figure out in this leg over here what the voltage is. Figure out what the voltage is over here on this leg. What's the voltage over here? How'd you get it? So you did over here, V equals IR, V equals 2.3 times 3.5. Give me that voltage, please, again. 8.05 volts. Yeah? In parallel, voltage remains the same. So what I can tell you is the voltage across this guy is also 8.05. Is that going to let me calculate I? Yeah, that'll let me calculate the current here. So here, 8.05 equals I times 5.2. What's I come out to be? 3.85? 3.85 amps. Yeah? We all good with that? I don't think that's right.
That's one's third. That's one's third.
Got ahead of yourself.
1.55.
1.55 sounds much, much better. 1.55 amps. So I got the current comes out in red, and then it's going to divide into these two legs now in green. 1.55 amps comes through one leg, 2.3 goes through the other. How much is the actual red, the current coming out of the battery? How much must it be? 3.85. Emily.
Okay, why is 3.5 in far on that?
All the way over here?
Yeah.
This over here is associated with that resistor. 2.3 amps flows through it. Resistance of 3.5 lets me get the voltage drop across this resistor. Voltage remains the same in parallel, so I can take that 8.5 and I can copy it over to that resistor too. which lets me figure out its current. Now I can add those two together and get the total current that's flowing out of the battery. Yeah? Well, now it's just plugged up. This is 3.85, so I can come down here. EMF equals 3.85 times 9.89 plus 1.3. EMF equals, with correct sig figs and units, please. I'm sorry? 43 volts. You got 2 sig figs in this problem. What was given? So your EMF comes out to be 43 volts. Dividers. The purpose behind a potential divider, and I'm going to set up a potential divider to start out with 2 resistors. Okay, you have a battery. Let's assume no internal resistance, so it's a nice little perfect battery here. Okay, 24 volts. Now, a potential divider would be something like this. The entire purpose behind it is, let's say your light bulb, I have a filament lamp drawn down there, it's kind of in the second position for the resistor, can't take all 24 volts. If it has 24 volts, it actually drops all the way across that. Remember, if it was just itself in that circuit, all 24 volts would drop across that light bulb, we'd blow it out. Okay, so you don't want to hit it with all 24 volts. You need to step down your voltage. You got to step down your voltage. The way you do that is by putting some resistor in circuit with it. And it doesn't matter before or afterwards, okay? It's going to distribute evenly before or afterwards. It doesn't matter, right? V equals IR, current remains the same, means whether you had it before or afterwards, the voltage drop is going to be the same, no matter what position it's in. Okay, so don't get freaked out if you feel like they're flip-flopped, all right? But having another resistor in there means this guy's going to get less voltage. I mean, just as an example, let's say that this has a resistance of 5.2 ohms, okay? Say it has a resistance of 5.2 ohms, right? And just for argument's sake, let me give you an ammeter because sometimes current is a lot easier to measure than the resistance of a light bulb. So you have an ammeter that's giving you a current of, let's go with 1.5 amps. What's the voltage drop across my filament lamp, my light bulb here? Come on. Can I figure out the voltage drop across that guy? Yes, how? Yeah, this is V equals IR, right? This is V equals 1.5 times 5.2, giving me a voltage of what? 7.8 volts. Leaving how much to drop across my filament light bulb? 16.2. I effectively reduce the voltage dropping across it. I effectively reduce the voltage dropping across my filament light bulb. If I need to reduce the voltage a little bit more, I stick a bigger resistor in. More of it drops across the other bigger resistor, less of it drops across the light bulb. That's that general principle. The bigger the resistor, the more voltage that will drop across it. Now, the bigger the resistor is in comparison to the others, I guess I should say. In comparison to the other resistors in the circuit. Okay, whenever you were setting up your circuits in the lab, a few of you had the issue of, and it still would have worked out because I know a couple of you had some really small resistors in there and it worked. If math errors didn't occur, some of you had a 100 kilo ohm resistor somewhere in your circuit, right? And then you also had like a 100, or let's say 1 kilo ohm resistor, or a 0.1 kilo ohm resistor in your circuit, right? And what you found was, if you turned your power supply all the way up to 13 volts, you found that, I don't know, say 11 volts dropped across the big guy, only leaving, sometimes even if there's other resistors in there, microvolt or millivolts to drop across the smaller resistor. And it was so small as we got lower and lower. It's all relative to one another. This is the type of circuit that we use, though, to prevent from burning out electronics. Right? This is the idea that computers use to not fry themselves. They have a resistor in there with the one purpose of preventing you from frying whatever circuitry is down here. Okay? It's going to use up some of the voltage before you get there. Okay. It has to be in series. If it's in parallel, the voltage remains the same and we got issues. Okay. Yes?
If you like put another lamp in there, would that work as a resistor or not?
It would divide the voltage effectively. Yes, it would divide the voltage effectively. Now, where this really becomes useful, okay, where this really becomes useful is with variable resistors, okay? Where this becomes very useful is with variable resistors. Here's what I mean by that. Same exact circuit, okay? Same exact circuit, 24-volt battery, ammeter, the filament lamp, and I'm caring about the voltage drop across that filament lamp here. And I'm going to install in a variable resistor in the circuit with it. Now, a variable resistor there's lots of different ways to make it. One of the simplest ways is you coil up wire right into a coil, and the tighter you squeeze that coil, the more that it's touching, right? And so in essence, the current doesn't have to go all the way around the wire, all the way through, right? It's able to just kind of skip over it, so the resistance drops dramatically. Okay, the more you turn it and coil it up. And the more you loosen it, the more the current isn't allowed to kind of skip from spot to spot to spot. The more it has to travel around and around and around and around. Remember, resistance is rho length divided by area, and so whenever you loosen it, the length going all the way around all those times on that piece of metal inside, the length becomes a lot higher, meaning the resistance is a lot higher. That would be a simple variable resistor. Right? So you tighten it, squeeze everything together to where the current can't just jump because all the pieces of metal are not touching. Right? So it just jumps all the way through. Or you can loosen it to where there's gaps between the metal, right? And now it's a very loose coil, all right? So it actually has to go around. You can't just skip all the way down through. That would be a variable resistor. With a variable resistor here, I can dim this light. I could either turn my variable resistor all the way down to 0, okay? Turn it all the way down to 0. How much voltage is going to drop across the sky? 24 volts, right? Or I could, let's say, turn it all the way up. Lots of variable resistors will get up to somewhere in the mega ohm region, right? If this variable resistor will go all the way up to, I don't know, say 10 mega ohms, how much is going to practically drop across your light bulb? 0. Everything's going to drop across the variable resistor, okay? How many of you have dimmers in your house somewhere? A dimmer for a light switch. This is what this is. They stick a variable resistor in series with your lights. So whenever you take that dimmer and you slide it down, right, so you're trying to dim the lights, you are turning up the resistance in the variable resistor, meaning more of the potential difference is dropping across the variable resistor, leaving less to drop across your light bulbs, I'll say, or dimmer. Okay? But whenever you turn the lights up, right, that means that you're turning your variable resistor down to practically 0 eventually if you turn them all the way up, right? And the effective resistance becomes 0, meaning all the potential difference can drop across your lights, meaning they're the brightest they can be at that point in time. A word of warning. Whenever you turn, let's say you don't flip the switch. How many of y'all actually do flip the switch whenever you're leaving a room on your, sliding dimming lights? I got 1, 2, the rest of y'all, you just dim them all the way down to nothingness. If you dim your lights all the way down to 0, are you still using power?
Yes.
Yes. Yes, you are still eating up power. If you dim your lights on a slider, right, all the way down to 0, that means you have turned up the variable resistance up high enough all the potential difference will drop across it, and none of it's going to drop across your light volts. Well, that's nice and all. You don't have light coming out, but the variable resistor is still chewing up power. Okay? It's still using electricity. There is still an electrical flow in your circuit. So what you'd want to do, don't just dim them all the way down. Actually still flip the switch, right? To where you have a open circuit at that point in time, thus you're not using power. Kim?
So, what if those little lines are just running in parallel?
These little lines right here, lots of times we will draw lines out, and I wanted to go ahead and show you this. Just to designate, we're measuring the voltage across this filament length. Okay? If necessary, you can think about imagining putting a voltmeter in parallel. Okay, putting the voltmeter in parallel. All right? Now, this is the basic potential divider. It's pretty simple. Let me come over to sliders. Now, sliders deal more with potentiometers. They actually have 3 wires coming out. It has a variable resistor built into it. Okay? Has a variable resistor built into it. You'll see pictures drawn lots of times, something like this. Okay? With a ammeter up top. Now, all that other wire and arrows pointing for is not for the current to travel across. It's just trying to show you the percentage, okay, that is going to drop across what you want it to drop across. 24 volts. So the picture I've drawn here. What percentage of the voltage in this picture is going to drop across my light bulb estimate point? Well, give me a fraction. What would you say? No, not all of it.
Is that a resistor?
Here's the variable resistor. If the wire was right here, if the wire connected all the way down to the bottom, how much would drop across? 0. This in your diagram is labeled as A, right? Let's label as A. Okay. This up top is labeled as B. Yeah, I put the ammeter up top instead of down the bottom. Doesn't matter. Okay. Okay. Go from where the wire comes out. That's what I need you to see. Technically, I drew my battery backwards. We're okay. Come from where the wire splits off. If the arrow points all the way at the base, in series, doesn't matter if it's on top or bottom.
No, it's on the right side of it though.
I'm sorry?
Does it matter that it's on the other side of the charger wire?
Doesn't. Current's going to remain the same here. This is, it looks like it's parallel. It's still a series circuit. Okay? It's a way to graphically show percentages a little bit easier. Okay, so let me explain it and try not to freak out. This isn't a parallel circuit. This is a graphical representation of this. Okay? Except I'm able to tune my resistor. Instead of drawing a variable resistor and having to give you numbers in there, I'm showing it in terms of slider. The advantage here is with this kind of picture representation, I'm able to give you quick percentages where you don't have to think about it. At the bottom, you have 0 volts drop, and at the top, how many volts it drop? 24. So at the bottom, if what we had labeled in your picture, C, was down at A, this voltmeter would read 0 volts. In other words, all of the voltage would drop across the variable resistor. The variable resistor has been turned all the way up, if you will. Okay? If point C, the little arrow drawn, was all the way up at B, that means I've turned the variable resistor all the way down. I've given it 100% all 24 volts is going to drop across my light bulb. None is going to go to the variable resistor at that point in time. None is going to drop across the variable resistor. Okay? These are just percentages, just pictures.
Why does it
It's not really a why here. This isn't a, and some might argue with me, but this isn't a technical picture like this might be, okay? Where I'm actually showing every little component of the wire and how it's working. Instead, I'm trying to summarize this into more of a nice little pictorial form to where I can show you the slider idea, where I can show you percentages. In other words, if it's all the way down at A, all I need you to remember is if it's all the way down at A, none drops. If it's all the way up, all of it drops across the light bulb. So C is about, I don't know, say 2/3 of the way. 2/3 of the way right now. Everyone get that? Everyone, can you kind of see that? And I'm just estimating here. Okay? But it's about 2/3 of the way, meaning what's my voltage come out to be? 24 times 2/3. What is it? 16 volts. This is a way to actually show I can tune the resistor to everything different. If I didn't draw it like this, if I wanted to draw it like that, I would have to draw a brand new circuit for every time I change my variable resistor. Okay? Change it a little bit, have to draw a brand new circuit. Instead, let's get the variable resistor out of there, and let's just talk about percentages dropped across the light bulb. How much drops across the light bulb? So we don't even have to worry about the variable resistor there. Tune the variable resistor all the way high means the slider's going all the way down to the 0 point. Tune the variable resistor to where it's incredibly low. That means that we're dropping almost all of it across the light bulb. Okay? It's a pictorial way to show how much drops across whatever object you're trying to power. Here, a light bulb. Emily.
Can you try another one?
Alright, so I'll put the ammeter in a different location. Slider, right? Now let's come down a little bit. Light bulb. Let's stick the ammeter there. And a voltmeter. Ammeter is in series with the light bulb here, just like it was in series up top. I know it's kind of weird. It looks like it's in parallel. It's a pictorial way of explaining it. This is in series with the light bulb, right? How much current goes through the light bulb. Voltmeter is in parallel with it. If this is let's make this a 24 volt battery. What do you think this picture is trying to tell you? How much is going to drop? 1/4, 1/8? About a fourth? Yeah, that's a little bit less than a third, so let's go with, this is about a fourth. So what is your voltmeter going to read? 6 volts. It's 6 volts that are dropping across this light bulb. Okay? 6 volts dropping across the light bulb. Which means, if you will, if this helps you understand it, that means here's my other 3/4 dropping across the variable resistor. Okay? 3/4 is going to be how many volts? 18 volts there, right? It's going to drop across the other part of the slider, or the variable resistor there. Get back to my 24. Do we need me to draw another one? Are we okay with this?
So is it always going to go from like the top to the bottom, so like we have to go to the top? Do you know what I mean?
the closer to the top you get,
Yeah.
the more that
Like if it was sideways, like that whole thing turned sideways and not being
always look, always look where the arrow is coming from. Okay, the arrow is going to show you the direction that you're looking from. Okay.
So is it like, when it's closer down, it's like, what else would be closer? So,
Correct. Correct. Yeah, you're gonna get more voltage drop across whatever light bulb you want there. Can
You can think of, this is, I just wanted to, you can think of like the resistor being cut where the arrow is, so the part under the arrow is being in parallel with the light, and the rest of it's in series. And so that part that's in parallel with the light has the same voltage as the light.
Yeah, if I were designing this, okay, this type of drawing, what I would help emphasize this is I would get rid of that wire right there. This is just me personally. I'd get rid of that wire right there to show you current has to go through the light bulb and then drop across the rest. All right, and so this is about 3/4 of it taking it up, right? So this is about 3/4, so you take up 18 volts here. How much is left over for the light bulb? 1/4. That's how I personally would have designed this type of picture. But you know, I am not the physics gods. Those who have come before me have decided that there should be wire connecting those. It's still in series. It's not in parallel. That's the whole idea with potential dividers. Because if it's in parallel, voltage remains the same, and this doesn't work. We're not dividing the potential difference. It all stays the same. All right. IB question, filament lamp rated 12 volts, 6 milliamps. So they're telling you about the actual filament lamp right here. Just light's potential difference is 6 volts. Student sets up an electric current to measure the IB characteristics of the lamp. Circuit shown below, things are not right. Battery has an EMF of 12 volts, no internal resistance, meaning the EMF is the same as the terminal voltage. That's what's actually coming out of the circuit. Ammeter has negligible resistance. The resistance of the voltmeter is 100 kiloohms. Explain, without doing any calculations, whether there's a position of slider S, which the lamp will be lit. What'd you get? Well, no is correct. No is correct. Why? Yeah, the voltmeter is going to steal everything, period. No ifs, ands, buts about it. All right. The voltmeter has a resistance of 100 kiloohms. The slider has a variable resistance where it maxes out at 15 ohms. And we can assume here that the slider, the variable resistor, has to have a larger potential difference, right? A much larger potential difference than our light bulb. Otherwise, it wouldn't use up all of the potential if we took the slider all the way down to what we call position A on our previous, on our notes, right? So the light bulb has to have a much smaller resistance than 15 ohms. It needs to be like 0.1 ohms is what it needs to max out on. So it has to be, no matter what you do, all of it's going to drop across our 100 ohm guide, right? Everything drops across the 100 ohm guide. I don't care where you put the slider. Everything drops across the 100 ohm guide. Or excuse me, 100 kilo ohm guide. Estimate the maximum reading of the ammeter. The slider doesn't matter. The light bulb doesn't matter. All that matters is that voltmeter. That's all that matters here. If you need to draw this out a little bit better in a way that might help you think of this, remember it's still technically all in series here. Okay, so I've got a battery, right, coming around. I've got a light bulb. I've got a voltmeter, and then I've got a variable resistor, ammeter, and back around to my battery. That's me taking the slider out of the picture, okay, just to try to get the gist of what's going on here. this variable resistor goes anywhere between 0 and 15. So this can max out at 15 ohms and go down to 0, 0 to 15 or 15 to 0. This voltmeter has a 100 kilo ohm resistance, and this guy has to be less than, it has to be much, much less than 15 ohms if the slider or the variable resistor was going to do its job in the first place. So I can neglect the light bulb, and I can neglect the variable resistor. I don't care what you do to those two things. I've got a 100 kilo ohm guy in series, everything's dropping across that. Having these guys tacked on, 100 kilo ohms is, kilo means tack on 3 more zeros, right? This is 100,000 ohms. 100,015 ohms just doesn't matter, right? Or 100,015.1, turn the slider all the way up and include the light bulb. Who cares, right? Those two numbers are so small you can neglect them completely when compared to the voltmeter. Heck, significant figures, right? These guys here, I mean, it just doesn't matter. Whenever you did V equals IR, you'd have to drop those anyway. Okay? You have to drop those anyway. Okay. Good question. If it's not much less than, if it's not much less than 15, we need an order of magnitude less. Okay? Then our variable resistor wouldn't be able to do its job. We want the variable resistor to be able to be tuned up so much higher than the light bulb that it's going to use up pretty much all of the potential difference. Well, let's think for a second. If the light bulb had a resistance of 15, okay, if it had a resistance of 15, I turn my variable resistor all the way up. So now I've got two resistors, each of 15 ohms, right? This is a 12-volt battery, meaning with that variable resistor turned all the way up, I would have how many volts dropping across each of them? 6. Does that make sense? If the light bulb here was just 15, I'd turn my variable resistor all the way up. This is neglecting the actual part of the question here. I'm explaining a different set, or a different question. I turn my variable resistor all the way up. Or I took the slider on your lights in your home, for example, and I tried to dim the lights all the way down. Taking the switch to all the way dim would only cut the brightness in half. It would still be 6 volts dropping across. Yeah? If they were the same. So I need to let my variable resistor get bigger. Not just a little bit bigger. Might not get the lights dimmed all the way down to nothing. I need to allow it to get much, much bigger. Right? To where, in comparison, the light bulb might as well not even count at the circuit when compared to the big variable resistor. Does that make sense to everyone? Yeah? Yeah.
Just about the light bulb, is the range that a light bulb is that the maximum, like the voltage, is that the maximum number, the minimum, or like always the same?
All right. What you're getting from a light bulb, right, it's going to give you, it generally reads in watts, right? And some of them will also write down how many volts it wants to take in, which it just takes straight wall voltage, right, for the most part there. The light bulbs that you're going to plug in into a slider circuit work slightly differently. But what it's rated at is what it will operate at under maximum settings. Okay. Now, could you technically, if you took it out of the wall and hooked it up to another circuit, could you try to crank it up a little bit brighter? Yeah, right. But you can pretty much assume in our society that you're going to have what voltage? 120 volts, right, coming out the wall. So that's constant. That's your battery at all points in time. Now, for this question, since the voltmeter is in series with it, I can assume all voltage drops across the voltmeter, meaning that I've got a V equals IR, right? That's a 12 equals I times 110 to the third, right? Which gives me a current of what? Current of what? You're going to get a few zeros in there. How many? should be 0.012 milliamps. Double check. I mean, number of zeros, fingers. 3 zeros. 1, 2, 3. 1, 2. Tenths. Just like that, right? Is that what you found? Is that what everyone else found too? That was off slightly. A very small. That's the best you can possibly do. You can neglect everything else. And that's what you're gonna. That's what you're gonna have. Okay. For example, if you put in, instead of 100 times 10 to the third, you put in 100,015, right? You put in 1,000,015 and divide it over. You find 0.0001209, something like that, or less than that. It wouldn't even matter. It wouldn't even play a factor in your sig figs. Okay.
When you go to you can't use those plugs, your plugs in now. Is it because there's a different voltage from now?
Correct.
And so when they like give you plugs to change it, do they have an issue?
Yeah, that whole, has anyone gone to Europe and seen, or know what I'm talking about? You bring either a surge protector that steps down the voltage, right? Or you bring a plug that steps down the voltage. All it is a potential divider, except we don't need a variable resistor in it, okay? It knows how much your appliances need, 120 volts, right? And it knows what's coming out from Europe, it's constant too. And so it puts a resistor in series before everything to use up the correct amount of voltage. Okay, now it's way more complicated than that, because depending on what you're plugging in will vary. So they do have to have a variable resistor in there, and so it has to fine tune itself. But that's the general idea. It's a potential divider.
So if you're getting, so you need to change to like 20, but if you're getting 100 out of the wall, there's no to run.
Correct.
And also,
Closely correct.
I guess you could.
There are other tricks up our sleeves. We can sacrifice a few other things to up voltage, but those are other amplification tricks. Okay.
Also, if you're dealing with, say, converting 140 to 120, you're wasting energy, right?
Correct.
So that would be the equivalent of using that volt that needs 80 volts, 120 volts. Because whatever the 140 that you're just dropping, you're not using.
Yeah, you have another resistor in series that is purposefully wasting energy. That way you don't burn out whatever else you got. So yes, you are wasting energy in that case. All right, let's draw the circuit correctly here. You're going to have. That's not going to work out for me. Circuit looks something like this. Voltmeter parallel, ammeter in series. They like the ammeter here, the light bulb. Does it really matter? No, it's all one big series. But technically, in the slider notation, they like the ammeter right next to the thing you're trying to measure the current on, right next to the light bulb. Okay. Questions?
This is kind of right with the arrow.
No, but I would try to keep it the same as the picture before, which was halfway. I think I'm a little above halfway, but I'll try to keep it the same. Only change the things that are incorrect. Don't change anything else.